Fusion is a great stepping stone. It's a great starting point, but it's super important that you also get out there in machine shops and you actually learn the fundamental of machining, because it's not just about code. There's science to how material gets removed.
Welcome to the HPA Tuned In podcast. I'm Andre, your host, and in this episode, we've got Matt Bernasconi, or as he's known on Instagram, Matt826, joining us. Matt is a master of 3D modeling, CAD design, and CAD manufacturing, CAD programming. This is something that's become a lot more prevalent in our industry as access to this technology has continued to come down in price. And while Matt works at the upper end of this industry, specifically he is working at Kibitech, who build some amazing pre-runners as well as really high-end aftermarket suspension components for a range of popular trucks. We're also seeing that this technology is creeping in even at the enthusiast level, with the access to free or cheaply available software like Autodesk's Fusion 360 for home enthusiast use. We're really seeing this transform what the average enthusiast is able to design and develop in their home workshop or garage. And in particular, when we also add to this the access to technology such as 3D printing, really what we can do with our own project cars has become so much more involved or so much more intricate, and the end results that we can produce obviously that much better. However, when we start this journey, of course, there is a lot to learn and a lot that we need to understand before we can jump in and start designing parts. So we talked to Matt about how he got his start, how he started using CAD, how he moved into 3D modeling, as well as how he ended up getting involved with programming CNC machinery. He's had a really interesting career, culminating in his position right now at Kibitech. And I know I've personally spent hours scrolling Matt's Instagram feed looking at some of the most insane parts that I've seen in the automotive industry, and I'd certainly urge you, if 3D modeling is of interest to you, jump in and check it out. We'll of course put a link to his social media account in our show notes. Now, before we get into our interview, for those who are maybe new to the podcast, High Performance Academy is an online training school. We specialize in a range of performance automotive topics, including engine building, engine tuning, wiring. Relevant to today's topic, we also cover some fabrication topics, including the fundamentals of motorsport fabrication as well as motorsport TIG welding. If you are interested in learning these skills, I'll put a link in the show notes to both of those courses. And I know that a lot of enthusiasts who are working on their own cars would maybe think that the skills of fabrication are out of reach. Maybe it's something that you can't learn. The reality is there's no magic here. And if you understand the tools that are required for motorsport fabrication, a lot of which are cheaply and easily available, and you understand how to use these tools properly, how to plan out your projects, and how to then action those plans, then it's totally within the capability of most enthusiasts with a little bit of patience and an eye for detail. So again, we'll put a link to those two courses in our show notes. And as a special deal, you can use the podcast 75 coupon code. That's going to get you $75 off the purchase of your first HPA course. All right, with that introduction out of the way, let's jump into our chat now with Matt. Okay, welcome to the podcast, Matt. Thanks heaps for joining us today. And as we usually do with most of our guests, let's just get started by getting a little bit of background on how you got involved with the automotive industry, and particularly your skill set around 3D modeling.
Hey, Andre. Yeah, thanks for having me, first of all. I've always pretty much been obsessed about cars and computers since the day I could remember. I did have an opportunity to work for a shop when I was 17 years old. And it was basically just general machining and kind of like a grunt worker. Didn't do anything other than grinding, plates using iron workers, conventional lathe, a Bridgeport. And I was, like I said, pretty young. I got kind of in the mix with that. And I guess that's kind of how I got involved initially with the automotive industry.
So that's quite deep for a 17-year-old. You're straight into learning how to use a lathe and a mill. And is that something that you were passed that knowledge on from whoever you're working for?
Yeah, I mean, when I first started, I guess if you go back a little bit further, my first introduction to like anything automotive at all really was myself just playing around on the computer. And in high school, I started using CAD. So the high school I was in introduced a CAD program. And it was actually by complete accident that I actually enrolled into that program. I originally wanted to do auto tech because I was obsessed with cars. And that class was filled. And so they said, well, here's an AutoCAD class. You should take this. And I said, sure. I didn't have any idea. I didn't really have any guidance growing up saying like, hey, you need to do this or that, or engineer peers or anything like this. I just knew I liked cars. I like computers. And I essentially just wanted to get into a automotive class, where I can work on cars with like my friends and stuff like that. So I signed up for that class. I showed up and there was just like a lab. And I was like, it was a computer lab. And I was like, well, where are the cars? And it was instructed by the same teacher that was instructing the auto shop class. Mr. Kiley was his name. He was kind of like, no, there's no cars here. This is the computer lab. We're doing CAD. And I was like, well, what does that mean? He's like, it's computer aided design. It's drafting. And I was like, okay, well, that sounds cool. I could do that. This was like 1999, year 2000. So you have to remember, like, Toy Story was fairly new. It was like 3 or 4 years old. And so anything like with the idea of putting something in the computer was like pretty awesome to me. Like, just watching those films is like, oh, computer animation. That's what I thought initially. So I was like, yeah, I'll give it a whirl. And that was basically my introduction to CAD. I remember the coolest thing was just drawing a cube and like cutting a circle out of it. It was like the most basic thing. And then like kind of spinning it around. I'm like 15 years old, right? And I'm just like, whoa, like this is just mind blowing for sure. So I was like, this is one of the coolest things ever. A classmate of mine pirated a version of AutoCAD, and every day after school, we would go to his house and we would draw everything in our rooms. And literally, I eventually got my own little pirated version on Napster, I think was the program at the time. And I just sat in my room and I drew everything from the spools on my bed to the rails on my closet door, even the blankets, through learning how to use CAD. When I got my first job, actually my mom is the one who got me the job. She said, hey, this guy has a speed shop and it's kind of hard work, but there's race cars involved, this and that. And I was like, okay, sold. I'm going to go there. And I started working there. They kind of just trained me on site. It wasn't anything special. It was really just manual labor. Like you just show up, you stamp a bunch of holes in some plates and you go home with a paycheck. And I just liked the idea that maybe there'd be a chance that I could see a race car come through there. And I'd never seen a race car in real life. It was kind of like, it would be really cool to see one, So for about 3 or 4 months, I was just stamping holes and just doing manual machining. They just teach me on site, like, turn this button, you're going to spin this, it's going to turn this, and, on the lathe, or you're going to drill some holes on this plate. And then one day, I think the owner of the company was working a full-time job. So this was like a side gig for him. He had to update a CAD drawing because nobody at that shop knew how to use CAD. And so I remember it was late one night. He shows up, he turns on his computer, and I see the AutoCAD logo, and I'm like, hey, AutoCAD, I can do that. Well, can you do this? And he pulls up like a little plate and it has like 4 holes, like a standard bolt pattern. And he goes, can you widen this 1/4 of an inch or elongate these holes 1/4 of an inch? I was like, yeah, I can do that. And, I was obsessed. So I knew all the quick keys. And it took me about 15 seconds to modify everything. And he was like mind blown. He was, okay, well, listen, here's the deal. I'm going to give you a $2 raise and you're going to have an added title to your job. You're not just going to stand there and machine and do little things. And I said, okay. So from that point on, I was known as the CAD kid. It was a lot of fun. we were at the races every other weekend. And it gave me a lot of insight to what it takes to campaign a race car. And so I realized that a lot of the parts I was making in the back, I could avoid if I just updated certain drawings a certain way. So one of my incentives was fix the drawings and I could do less work out back.
So simplify the entire process
Yeah.
by getting the drawings right.
Yeah.
Okay, so how long were you with that company for?
I was with that company for a decade.
I imagine you've learned a lot of new skills over that time. Are you still predominantly involved with the CAD work and the machining, or had your role branched out over that time as well?
No, so I just worked for that one company. And like I said, I did the 2 years in high school for CAD. I used Autodesk AutoCAD. And in 2004, I wanted to kind of expand my knowledge in just computers. So I actually signed up to the junior college. I did a class for CG 101, which is basically like Photoshop, Illustrator, InDesign, more like graphic arts. And I learned a lot. I learned a lot about colors and, shades and how everything works with that area. And I feel like that plays a big role onto what I do today also, because I still use that day in and day out. And then when I was 19 years old, right around 2005, the company I was working for, they needed to bring some machining in-house. We ended up buying a Haas lathe. And then that's when the owner was kind of like, hey, you're really good with CAD. I think you should give this a shot. I think you should try to program this machine. I said, okay. Did about 6 months of control training. And at 19 years old, the machine got delivered. They set it all up. It was super nice. And I remember I walked up to the machine and the owner goes, okay, let's turn it on. Let's make something. And I was like, sure. And I go running to the machine and I'm like looking at it and I'm like, holy crap. They never taught me in school how to turn on the machine. And this is bad. So I was like, okay, I need to call somebody for help. Pretty much after that, I kind of just ran with it. And I was like, okay, I got this. I'm just going to program this. And it was just a lathe. So it's 2-axis. So the idea of spending, $5,000 or $10,000 on software to program it was out of the question. It was like, we're not going to spend money on software. You just have to type the code in.
All right, let's just stop there and pause for a second and dive a bit more into this, because this is just on the fringe of my understanding, and I'm guessing there's probably a few listening to this that are in a similar position. So I know that a lot of people have this misconception that with CAD or 3D modeling, you design this component and then just press print and it just goes to the lathe or the mill and out pops your part. But this programming, there's a bit more to it. There's another step in between. And you've just talked about software versus manually programming the lathe. So what does that actually entail? How does that sort of link your CAD design to how the lathe will actually machine that finished component?
Well, to be honest, I feel like they're just two different entities. I don't really feel like, well, for sure these days, it's a lot easier to get involved with machining, but it all comes down to G code. And G code is basically the language that the machine understands. You have to understand too, the machine is nothing but a fancy calculator. It's not a computer. A lot of people think that you see this DRO, digital readout, and you're like, oh, you just plug something in there and you press go. If something happens, it's going to stop. It doesn't. It's a calculator. If you tell it to go 20 inches this way, it's going to go 20 inches that way. And there's no safety protocol that's going to keep it from doing that. So the first thing I would say is the G code is essentially what the machine relies on. And if you enter the G code in there correctly, then the machine will output the right information and get the part going. But just by hand typing it, you can hand type it incorrectly. Just like on a computer, if you have CAM software, computer-aided machining software, it can output code that's incorrect also. And that will cause a collision as well.
So that can break some expensive tooling or damage the part that you've just about finished
manufacturing. Or even damage yourself. You can get hurt for sure. I don't think, machines are fun. You can do so much cool stuff, but they are dangerous. I mean, they can cause some damage. If you're lucky, it's very minimal, but most of the times, when you talk about a machine crashing, you're talking of thousands of dollars at a time, talking thousands of dollars in repairs, thousands of dollars in loss in productivity. So it is a very, involved thing. I was fortunate that when I first started machining, they kind of forced me to use, to learn programming, not to just jump into computers and say, hey, put it in the computer and it's going to print out a code and you'll be good to go. Because I would be lost, if I didn't understand the code. And so for 2 years, I hand wrote code. I literally sat at the digital readout and typed in hundreds of lines at a time. And I memorized all the codes, all the M codes, all the G codes. And so if I needed to make something, I could literally write a code faster than going to conventional and just trying to do it by hand, It was second nature.
Would I be right in guessing that these days with computer-aided machining and the advances, maybe some of that manual programming skill has been lost by a lot of people in the industry now?
For sure. I think there is a misconception that you can just get a software and you can become a programmer. And man, when I was growing up, if you had the title of a programmer, it was a big deal. Like, people work for a long time to get that title of a programmer. You have to, there's stepping stones, right? You start off in the very beginning, like if you were to go to a machine shop, you start off in the very beginning, button pushing. You're just going to load a part. You're going to push the green button. It's going to come out. You're going to do an in-process inspection. And you'll do that for a number of months, if not years. And then you kind of graduate from that in the machine shop and you go into setting up, where you're actually getting the program, you're setting up tools, and you're doing first article inspections, essentially running the part that the programmer has prepared for you. And then when you do that for a number of years, then you are able to get on the computer and program a part. And then you're the person that hands the program to the setup guy. Then the operator goes from there. So there's like this, there's these levels to get to that programmer
sort of a
state.
hierarchy, if you like.
Yeah. And you have to kind of do these stepping stones, because if you miss one of those and you program something incorrectly, the operator isn't at fault here. The guy that's pushing the button isn't at fault. It's a programmer. The programmer needs to know all of these steps. He needs to know everything beneath him in order to do his job correctly. And a lot of times the software, like, we'll get more into Fusion and all that stuff, but programming on Fusion, I guess, is, to me, seems more like a hobbyist thing. It's not something that I would say, I can program on Fusion. I'm a programmer. I'm going to go to a machine shop. I'm going to have a career. I don't think that's how it works.
Is that maybe, and as you say, we're going to dive into Fusion 360 shortly, but is that maybe giving a lot of the enthusiast level modelers maybe a false sense of their capabilities and where they'd fit into industry, do you think?
No,
because obviously they haven't had the extensive experience that you've had at each step of the way to build up that full understanding. They're kind of just diving into one specific area, correct?
Right. Yeah. It depends on who is reading the terms, I guess, because Fusion, you can program, you can do it, and it's very, very intuitive. It's amazing how good it is, to be honest. Mm-hmm. And I think, like I said, for a hobbyist, if you're a guy in your computer and you have access to a machine and you want to machine something, quick and easy, that's the fastest way to get in there and do it. And it works for most people and most things. I think that you draw the line when you start talking about a machine shop. Now, I'm trying to watch my words here because I am still having second opinions. Now, Fusion is still very new, but I have been mind blown by what Fusion can do. So I'm gonna kind of stop a little bit, but I'm gonna say what you can do with Fusion and any software comes down to the sole experience of the person, not necessarily the software, but your bottleneck is going to be your personal experience and your growth and what you can do with that software, for sure. And Fusion is a great stepping stone. It's a great starting point. But it's super important that you also get out there in machine shops and you actually learn the fundamental of machining, because it's not just about code. There's science to how material gets removed and how you remove that material, how fast you remove that material, and what you do as far as being creative to hold that material to create what you're going to be making.
This sort of comes down to an aspect of not every component that you could design in the likes of Fusion 360 is going to be either feasible to manufacture, or if it's feasible to manufacture, depending on how the part has been designed and modeled, you could have a very complex machining process versus some slight tweaks would make the component much easier, quicker, and hence cheaper to manufacture. Is that sort of what I'm picking up from that?
Yeah, I mean, there's going to be areas where, like in the design process, where you might make a feature, so to speak, that can't be machined, right? I guess that goes back to the engineering side of it. But if you were to get a part from like a customer and they say, "Hey, machine this," then I think that it would be a little difficult in most cases. It just comes down to experience. I feel like, I don't think you can just get the software and just jump in and start making stuff. Like anything else, the more you do it, the more you learn. And that experience, you pick up a lot more if you're in an environment where machining is what they do.
Okay. Before we get too much deeper into this side of the conversation, let's just come back a little bit and sort of fill in the rest of your sort of background up to the point
Sure.
where you currently are working today with Kibi Tech. I feel like we've kind of
Yeah.
we've gone down a rabbit hole, which is absolutely fine, but just for the sake of completeness, because particularly those who are maybe following you on social media at the moment, your Instagram is all about these amazing components you're making for these next level off-road competition trucks at Kibi Tech.
Yeah.
And I want to sort of join the dots. How did you sort of get to where you are in your career right now?
Yeah. So in 2007, we got a pamphlet in the mail, and basically it was a pamphlet for Autodesk Inventor. And it was this new software. It's supposed to be way better than AutoCAD, which it is. And at that point, they're like, "Hey, do you want to try the software out?" I said, "Sure." When they came out and we purchased that software, they recommended that we go to Cative Technologies, which is a trade school for Inventor and 3D modeling. So I signed up for that. It cost whatever amount of money, and then was there for 6 months, 3 days out of the week. And it was a really cool program. I learned a lot there, a lot of the fundamentals for sure. From there, in that same business, I ended up doing a little bit of robotic welding, some fabrication. We built chassis for drag race cars, production welding, robotic welding, a little bit of everything really. And then right around 2015, I actually ended up leaving that company and going into aerospace as a programmer. So during that time at that business, I was actually doing lathe programming, mill programming, and multi-axis programming for machines. So throughout that decade, I did a bunch of that stuff, as well as fabricating and welding. And I was kind of just a jack of all trades for the most part.
Sounds like you've had the opportunity though to really build up a very diverse skill set across pretty much every element of what you're now doing as well. So you've got that deep understanding of not just designing a part, but actually what's involved in the machining of that part, and then how it integrates with fabrication and the rest of the chassis build as well. Would that be sort of a reasonable read on the situation?
Yeah, I mean, I learned a lot for sure. Everything from what it takes to be at the racetrack, as far as prepping for the racetrack, everything from manufacturing, making processes more efficient, and then obviously the manufacturing standpoint, the machining, the programming, and then building a product and then selling a product. It was all like a one-stop shop for the most part. And that was a good platform. But after about 10 years, it kind of plateaued, and I stopped learning a whole lot. It started becoming more kind of just monotonous, And so I ended up going to aerospace. I applied to aerospace company. There was a machine shop that was manufacturing gears for aerospace companies and military companies. And when I went in there, I initially went in as a junior programmer. And man, what a change of pace. It was nothing like I'd imagined. And I honestly felt like I'd made a mistake. And it was like starting from ground zero all over again, which was good because, I mean, you think you know everything and then you get put out of your element and then you're like, man, I don't know anything. So going to this company was pretty awesome. At this company, I knew that I would learn way more than I needed to, and then eventually go back to the performance industry. Initially, I told myself 2 years. That turned into 3. But it was a huge learning experience, and it taught me a whole bunch. And I think the biggest thing I wanted to learn was how the engineers in the aerospace industry make parts. And so when I got there, I was able to see blueprints of actual engineers and how or why they make parts, certain features that they add to certain parts, understanding. And sometimes we would assemble a whole assembly for a plane, or sections of it. So we would, go through the process of assembly, what it takes to do that, traceability, accountability. And the shop was also AS9100 and ISO, which means that they're military and aerospace contracts from the government. So it's pretty top tier stuff. On top of that, the facility that hired me on was really, really high tech.
A lot of expensive stuff that you're very unlikely to come across in the automotive industry outside of maybe Formula One.
Yeah, I mean, it's pretty crazy. You do get used to it and you understand the process, and eventually it kind of just sets in like a job, It's pretty cool to learn all of that. So after I learned all of that, I started freelancing, and my friend Peter is a really good friend of mine, and he was delivering batteries to Kibitech. And he was kind of like, hey, Matt, like, I know you want to be in this area and, you're really good with cars and trucks. And so actually I called Kibby and I said, hey, can I go down there for an interview? And he said, sure. So I showed up and I brought my computer, and he was kind of like, yeah, so what are you applying for? And I was like, well, I can do a little bit of everything. So he was kind of like, hey, okay, well, you said you can design. Let's see if you can draw something up. He gave me like an engine mount. And then he was like, all right, well, I'll let you know. And I was kind of just sitting at home, and I was like, I should really kind of try to capitalize on this. So what I did was I got that engine mount I drew up, and then I built a spreadsheet, did a parts list, then exploded view of it. And then going back to my computer graphics background, I did an instruction manual and parts list and added some graphics to it, and then basically made it a complete product. And then I emailed him and I said, hey, let me know if you're still interested. This is essentially what we could put together. And he was like, wow, that looks really good. Yeah, why don't you come down tomorrow? Sure. So showed up on Saturday, and I freelanced for Ryan for almost a whole year every weekend. Ryan was like, hey, you should quit your job and just come over here and start building cool stuff again. And, he was still kind of putting the business. And I said, well, if you finish all that, then let's talk. And he did. He took care of all that stuff. And he said, all right, let's talk. And I said, sure. And he goes, quit your job. And I said, okay.
And the rest kind of history. So
yeah.
How long ago did you sort of go full time at Kibitech?
I started full time with Kibitech in November of 2018. And the initial thought was we're going to bring in machines, and we're going to start a product line, and that's going to help with a little bit of revenue so that we can build more trucks and then help the process from there.
So from what I've seen on Kibitech's website, there's sort of 2 areas to the business, as you said, products. So basically bolt-in suspension upgrade components, for example, for some of the popular trucks. And then you're also building bespoke, complete, custom trucks as well for competition. Is that sort of about right?
Yeah. So initially, he does like luxury pre-runners, and he builds pretty much as nice as you can get them. Most of the customers, they just want the nicest luxury pre-runner truck. So initially, he was kind of just sourcing out a couple machine parts here and there, but they're hand fabricating everything. And really nice. Obviously, they're known for like their welds and their welding and stuff like this. So they had all that kind of taken care of, and they had prior CAD guys coming in and doing, small stuff, but I kind of stuck around the longest, and they knew that, Ryan knew that I could add the machining process to the whole business. And we not only decided to add a product line, but every truck from that point on was getting something custom, one off or whatever. And it was always like, oh, let's try to push the limit on the industry a little bit and see, if we can add this or add that. And something that trophy trucks are doing, we're trying to do the luxury pre-runners and try to lead some of the industry with new ways of manufacturing and adding just like a lot more personalization to every single truck.
One of the things I haven't heard you talk about here, which I'm interested in diving into a little bit, with a lot of the components that I'm seeing you design, there's an element of what would conventionally require maybe some formal training in mechanical engineering, that sort of thing. You haven't talked about any formal qualification in that area. Is that correct, or have we missed that, or is this just something you've really just picked up on the job?
Yeah, so Ryan's been involved with the off-road industry for a long time. So a lot of the engineering kind of falls back on him. And I have had a lot of years in learning the process and building other motorsports applications like drag race cars, for example. But those fundamentals, a lot of those don't work for the off-road industry. So I rely on him a lot to give me the information, and we work together and collaborate what it takes to build certain items that have already been done and proven.
Yeah, I think that's really valuable to just add in there, because we have a fabrication fundamentals course, and some of that comes down to designing a component that might be in a stressed application where if it fails, obviously someone could become hurt or even killed. So understanding the stresses involved and what you need to design, what you need to do to design a part that's going to be able to withstand that is obviously really, really important. And on one hand, obviously, you could go through a mechanical engineering degree and be able to calculate all of that for yourself. But a really valid way of doing this is to model what you're making around existing components in the industry that have proven to be up to the task. So there's always a couple of ways of doing it. I just want to make sure that people don't think that a 4-year degree is an absolute requirement in order to be producing aftermarket components in this industry. Now, coming back to the CAD side of things. So we've talked about 3 software packages so far. You've talked about Autodesk as the manufacturer, and they've got AutoCAD, Inventor, and Fusion 360.
Yeah.
Flip side of that is SolidWorks is also another really popular option. And can you for a start talk to us about the difference between AutoCAD, which you sort of got started with, and Inventor? Is this sort of 2D versus 3D, or solid modeling versus not? Yeah, can you give us sort of a lay of the land there?
Sure. One thing, Andre, on that last note, I know we were talking about the engineering degree and all that stuff. I just want to make sure that that's also clear. I think it's very important to have an engineering degree, to be honest. I know a lot of people say that it's not so necessary now, and I know there's a whole thing about, school costs a lot of money. It's super important to do that still, in my opinion. If you're going to follow this path, I think that's a shortcut. And if you're going to continue, and you really want to be involved and you want to get in there, I think the engineering route and going to a college, an actual college, is a faster route. I mean, I've been doing this since, like I said, from high school. I'm like going to be 37 now. And I feel like I could have chopped that in half had I gone to school. And I think school is very important. I think school shows a company that you're able to follow through with what you started.
I think that there's an element as well as it's going to depend a little bit on what industry you want to end up in.
For sure.
I mean, there'll be areas of this industry where you're not even going to get a foot in the door if you don't have a degree.
Absolutely.
It's just basically a prerequisite, and it is what it is.
Yeah.
The flip side of this, and probably more what I was referencing, is for the home enthusiasts that are coming through and doing our courses, they're probably not aspiring to end up in a position that you've got yourself to. And a 4-year degree to maybe design and manufacture some components on your own car, Yeah, I mean, yes, absolutely. If that's going to spin your wheels and you see value in that, by all means, have at it. But also, is at that level not an absolute requirement. So just to be clear, I'm not knocking a university education.
Yeah, for sure. Now I understand. Yeah, and the other thing too is the safety factor on a truck like this, like the pre-runners and the trophy trucks. It's not like a Formula One. Formula One, your safety factors are so much tighter. You know, these things, if they hit the curb too hard, they're exploding. But these
Yes.
trophy trucks, there's some things you can't account for in a computer. Like, you know, I saw a trophy truck hit like a 3-foot boulder head on and was able to go over that, survive, and continue a race. And that is some areas you just can't account for. There's certain things out there that a trophy truck or a luxury pre-runner is going to run into, and things have to be over-engineered a lot. A lot of that does come from experience. And like I said, I rely on Ryan. Ryan's, you know, we were able to work together and collaborate really well as far as building and using systems that have been proven to build nice structural components. And it's been a huge learning curve for me. But like you were saying, I mean, the computer does help a lot with this, and we do actually use some stress analysis for some items to help improve that. And a lot of it's being used for seeing the overall form of a part. You know, if we see any stress risers, then we can add or decrease material depending on what the graph is showing us. And all of that stuff is still being used. And the softwares today, they make everything so intuitive. It's not too difficult to figure out some of these things for these trucks if you put in the time.
Sure.
But everything does take some time. It's not like you can just throw some numbers in and 15 minutes later you have an answer. You'll work at it, and it takes some time to get there for sure.
Let's just dive into that term you use, safety factor. And I just want to sort of, you gave the comparison there of the F1 car, and obviously at the Formula One level, they don't want the cars falling apart under normal conditions, and there is a safety factor. So, if a certain amount of load or force is expected, then they'll have a safety factor that maybe the component will survive 50% more than that.
Exactly.
Or maybe in Formula One, it's a lot less. Mm-hmm. But the sort of where that safety factor comes in, the higher you want that safety factor, generally within reason, the heavier the component is going to be. It's going to be built stronger, which involves more material, which involves more weight, which obviously in any motorsport, weight is the enemy of performance. F1's that upper echelon. I mean, I'm guessing with the likes of your pre-runners, weight is still, I'm assuming, a consideration, but maybe not quite as much. And again, you've got that situation where you can't expect to encounter a massive boulder, so your safety factor is just that much higher. Is that sort of a pretty reasonable read on that situation?
Yeah, definitely. But yeah, if you the safety factor, like between the two, is just so astronomically different because there's so much things you can't account for. And so and these trucks are heavy. They're 6,000-7,000 pounds sometimes, and which is, I don't know, 2 or 3 race cars for the most part. So yeah, I mean, everything is super heavy. Steel, even the aluminum parts, they tend to be fairly heavy compared to other motorsports applications. So no matter what, these trucks are heavy. Now, like you said, everybody's always weight conscious. So you always want to try to, get to where you're going to be and still be as light as you can be within a certain margin. And I've seen pretty light trucks and I've seen pretty heavy trucks, and we've seen them work fairly similar. But at the end of the day, it's some of these trucks, they have to be able to finish the race. That's the biggest battle, is finishing it.
Yeah, reliability is critical, obviously.
Oh, for sure. 1,000 miles of like terrain is it's a lot to endure, and there's a lot of things that you can account for. So.
Okay. All right. Coming back to the earlier question, the Autodesk products, AutoCAD versus Inventor versus Fusion 360, and then SolidWorks. So can you sort of give us a high level view of the differences between what each is capable of?
Sure. Yeah. So Autodesk Inventor is essentially the same as SolidWorks. SolidWorks, and I think Siemens, they have like Solid Edge, and the same with CATIA. These are all about the same. They have like assembly files, they have part files, and then the computer essentially grabs a bunch of part files, like just the actual files, and they put it into assemblies, and then you kind of work in that environment. Fusion is a little bit more cloud-based. It's a little more streamlined. It's more intuitive in certain respects. And then I would say Autodesk and AutoCAD, that's more of a drafting software. You can still do three-dimensional stuff, but there's not an easy design tree like for engineering. So it's very difficult to do some of the stuff that we do on Autodesk, AutoCAD. Inventor, I feel like is a very strong program. And like I said, it's very, very similar to SolidWorks. It's kind of like a Chevy and Ford. They're same trucks. Maybe the color's a little different. The headlights are a little different, but it's the same thing. There's nothing different about it.
They get the same job done.
Yeah. I personally like Autodesk. Like I said, I've been with Autodesk for my whole life, essentially. But the cool thing about Autodesk is it's not just Inventor. They have Fusion, and they have a number of other softwares like 3ds Max, which is a rendering software. A lot of computer animation and computer graphics are done on 3ds Max. And so they have their feet kind of in everything. And a lot of their files are interchangeable and native to each other. So that helps with going back and forward with those softwares.
Okay. Fusion 360, one of the reasons we're sort of seen that's become quite prominent at the enthusiast level is because for sort of individual use, at least as I understand it, it's relatively cheap or even in free compared to some of the more professional products like Inventor or SolidWorks. So how has that become a bit of a game changer in that 3D solid modeling industry for the enthusiasts, as opposed to professionals operating at your level?
Yeah, so I'm kind of torn on that. Well, I was torn on that, I should say. If you had asked me that question 6 months ago, my opinion would have been completely different. But that being said, we recently hired a junior CAD designer here at our shop, and we set him up with Fusion because that's what he was comfortable with. And I saw his work; everything looked great, and he has pretty much blown my mind on every project he's done using Fusion. And I've gained a whole lot more respect for Fusion over the last couple of months. I think it's a great software. I think it's amazing the amount of value that you get with Fusion. It's just crazy. I'm borderline thinking that it could do almost everything that Inventor can. If not, in some cases, it can do some things better, which is kind of hard. It's a hard pill to swallow. It's a hard pill to swallow.
So that was going to be the next follow-up question. Where are the limitations in Fusion 360, and why would you choose Inventor over Fusion?
I'm not really sure right at this moment. It's one of those things I'm still trying to figure out. But overall, I've been very impressed with Fusion. I think the last couple of months, my mind has definitely been open to what Fusion can do. And the same thing goes for programming. I think for programming, I've used Mastercam, GibbsCam. These are all $10,000, $15,000 softwares just for machining specific, and then I've used Inventor HSM, and HSM is basically Autodesk's variant to adding machining to CAD software. So HSM can be added to SolidWorks. They have an add-on for Inventor, and it's the same thing for the most part. It gives you the same strategies and options and stuff like that. And then HSM is also in Fusion, but the Fusion one, for some reason or the other, works really, really good, if not better than the other two. They put a lot of effort into Fusion. It shows.
You're not really making a real strong case here for spending the bigger money.
I know. You're telling me because I spend the bigger money.
I guess, though, ultimately, 3D modeling software, you've mentioned we've talked a few of them, but there's a wider range out there. I'm guessing because it is a fairly mature technology, within reason, short of learning maybe the keyboard shortcuts and the toolbars, etc., you could probably take what you've learned on Inventor or Fusion 360 and transfer that across to SolidWorks with only a limited sort of learning curve. Is that right?
I think that Inventor and SolidWorks are a lot more similar than Fusion. Fusion is a departure for sure. The way that Fusion works is a little different. If you're in SolidWorks or Inventor, then you draw your sketch, you extrude it, you do this and this and this, and you type in your numbers, and Fusion, you're kind of doing the same thing, but you're kind of just dragging and pulling, and you're adding the same numbers just in a different way. And it's just, there's less,
slightly different workflow.
The workflow is different for sure. But I would say that if you're going from Inventor to SolidWorks or SolidWorks to Inventor, you can latch onto those two fairly easy. But if you were to open Fusion, you'd start to wonder where all your stuff is. And, it's kind of like a little different, but it goes the other way around too. If you learn on Fusion and you get thrown into Inventor or SolidWorks, then it's kind of like, well, where's this or where's that? Your parts and assemblies, they don't mean the same thing anymore.
I guess it always comes down with everything though to what you become familiar with.
For sure, yeah.
And you get to understand it, the ins and outs of it, little idiosyncrasies and tricks and tips, and you're obviously going to end up faster with that. I find exactly the same with the tuning software that I use day in and day out. I'm obviously faster with that software, and I can do a better job usually than something that I only see once every year or couple of years, even if the ECU has a higher level of capability, just to put a tuning analogy in there. Now, one of the sort of technologies we're seeing in the 3D modeling and machining world is the use of artificial intelligence or generative design to basically allow the computer to take some certain inputs and then design or develop the model around your constraints in terms of weight or strength or cost or whatever that may be. Is that something that you have any experience with personally, or you're utilizing? Do you see value in that?
Yeah, absolutely. I love generative design. I think it's awesome. I think everything about it's cool. I think it gives us a good opportunity to take a computer and see what it actually thinks needs to happen three-dimensionally. And I think it's the future for sure. But I think the only problem with it is accessibility. And that is being able to access generative design is a difficult thing right now, because you can't just have generative design and just have it free or pay a certain cost. Like Fusion, for example, you will have to get credits and then use it. And then if you want to use it again, you get more credits. So it's not fairly accessible to continue using it. And it's one of those things where I'd love to play with it more, but it's not as accessible as I wish it was. I like the idea though. I love it. Like even if you don't use it for the finished outcome, it gives you a good understanding of what is going on. And then even if you want to take that approach and, kind of work from an aesthetic value and say like, okay, well, this has to be here. We can give it this kind of styling cue and then kind of work with that. I think it'll give more parts an aesthetic and physical, like mechanical feeling all at once.
So breaking that down, maybe giving the designer an opportunity to see an alternative solution for that particular part that maybe wouldn't be immediately apparent. And then even if you're not using generative design, you can incorporate those design elements into your finished product. Mm-hmm. One of the things that we do tend to see with generative design components is they all have this kind of pretty intricate organic look to them.
Yeah.
Does that cause sort of issues around the actual machining processes? Because I can only imagine that the machining of these organic designs is going to be much, much more time consuming and involved than something that's more sort of conventional in its design. Or do you get to a situation where some of these components simply cannot be machined on a conventional mill?
I would say most of them can't be machined. Yeah.
Perfect.
Yeah. The thing is, like I said, I think it's great that it gives you an insight as to the general shape of a part mechanically and like how it works and the stresses. And you can use that as a guideline to create a part that can be machined. But, as far as manufacturing, you can always manufacture a generative design part through 3D printing, right? So you can always go metal 3D printing or plastic 3D printing, whatever the part's being used for, the carbon 3D printing. You can use it for that, but that's not really that conventional, like, you're not going to just 3D print some metal parts unless you're like Josh, the guy that was just on here the other day with his Alpha. That's a little different.
Josh Valens, yeah.
He's great. His project's awesome. But, it's difficult to kind of, have access to those machines or even pay to have something metal 3D printed right now. It's I'm sure in the future.
I mean, I'm guessing as well the likes of the metal 3D printing. While I know that technology is rapidly evolving, and even conventional plastic 3D printing, I mean it's not really something that's viable for a production scale manufacturing, is it? It's more for small scale one-offs or prototyping, as opposed to manufacturing at scale. Is that correct?
Yeah, right now it is, for sure. But it's like a 3D printer, your standard plastic 3D printer. Just about everybody has one now, I feel like. I have one and I use it all the time for whatever. But yeah, eventually the evolution of machining and manufacturing is so fast. It'll be to the point where everybody has one eventually. For sure, there's no doubt.
No doubt.
But for now, it's definitely good for rapid prototyping. It's also very good for. There's a lot of aerospace parts that are doing the 3D printing, because there's engineering that they're starting to do now, where they're designing features that can't be machined with that actual manufacturing process in mind. So they're just going that direction, and that's the only way to do it.
All right. Now, just we've sort of touched on this a little bit in terms of validating a component, in terms of the forces that are likely to be present, and how you sort of have the confidence when you manufacture or designing a component, I should say, that it's going to put up with hitting a boulder at sort of 100 mile an hour. With these 3D modeling packages, usually there's the ability to also run some analysis, finite element stress analysis on the component to sort of validate it in the virtual world before you ever actually manufacture it. Are you utilizing any of that, or does it just come back, as you've already talked about, sort of liaising with Ryan, talking about his experience, looking at the part and what you're expecting it to deal with, as opposed to the FEA side of things?
Yeah, I mean, so a lot of the times we have parts that have already been tested and proven through experience. And we have actually gone reverse engineering those parts, putting them in the computer and testing those parts, seeing what kind of stresses they are being put through, as well as seeing what their actually weak points are, if any. And then from that point, we use that as a baseline. And then from there, we can either change the material. In some cases, like if we're going from a fabricated sheet metal steel part and we want to make an aluminum counterpart that is going to replace it, then we can use the weight, we can use the shape, and then we can actually use the same stress testing to see with those numbers where we're at with the new counterpart that's made out of aluminum.
That's an interesting approach to it, which actually makes a lot of sense. And you've mentioned Josh Valens, and we'll link to his podcast episode as well, because there's a lot of crossover, and I think that would be interesting to anyone who's enjoying this chat as well. But one of the comments we had in that podcast with Josh was about the FEA side of things, in terms of it's kind of a garbage in, garbage out kind of deal. And what I mean by that is, it's going to be potentially very difficult for most of us at the enthusiast level to know with 100% certainty what stresses a component's going to actually experience. So the way you're doing it is kind of the other way around. You've got a component that has been out there in competition, it's up to the task. So then modeling that, it's not failing, so you can kind of get a sense of what forces it can withstand, and then you're using those inputs to then design the new component. Is that sort of it in a nutshell?
Yeah, pretty much. Yeah, and then we also have the newer products that are coming out. We're trying to kind of push the limit on where that boundary is. That line of limit. Where that part's actually going to fail, and it's pretty crazy. You'd be surprised how strong some of these materials actually are. I've seen some of these parts go through some havoc, and the fact that they can survive and still go on and on and on, it's pretty wild. But yeah, a lot of it is experience. A lot of it is learning from those experiences and pre-existing parts that have been put out there, put through their paces, and see how they withstand. And then also sometimes, it's not always glorious. Like, fortunately, we haven't had anything catastrophic happen or anything like that, but if a part gets damaged, so to speak, then we can look at that part and say, okay, even it didn't fail, but we saw it got damaged a certain way. We might change the shape a little bit so that it could either slide over something. Like, for example, if an arm were to hit a rock or something and it has a flat face, then we might add a draft angle to help kind of bring it to where that arm can actually slide over something a little easier.
So there's still iterations in your designs as you test them in the field and see how they're actually withstanding competition, essentially.
Yep.
And I'm interested to know sort of when you're looking at designing something like a trailing arm, you've got the ability to machine that out of a solid billet of alloy, or alternatively, you could hand fabricate that out of sheet metal. How do you decide which is the right option for a component like that? Because I've seen that you've kind of used both in certain circumstances.
Yeah, so the sheet metal arms have been around for a long time. I think essentially they started off like tubular arms with some sheet metal stuff. And eventually they evolved to just completely fabricated. Sometimes they have heims, sometimes they're just unibolts welded to the ends. But I think the whole industry is moving towards aluminum for weight and strength. And the aluminum is 70-75, so it's not just like your typical 60-61. 60-61 is great for a lot of things. The 70-75 has a higher strength than 60-61. It's also way more expensive. But 70-75 just, it's working out amazing, and we're able to make lighter components. And when we talk about a trailing arm, half of that is unsprung. So taking weight off of that is more important than pulling weight out of the cab. It's going to be more important for sure. So getting the weight down, increasing the strength and durability is a great thing. And there hasn't been any failures of those that I know of, as well, not with our stuff at least. But the only failures that come to mind are when trucks get totaled. But I mean, you're talking the whole truck is getting totaled, so it's not like the arm failed. It's part of the whole deal. The truck is damaged, the whole thing's destroyed. Shocks are bent in half. So if the arm breaks in that scenario, well, it is what it is. But as long as it wasn't the reason that all of that happened. But
naturally, yeah. I mean, you obviously can't design a component with a realistic weight that's going to be completely indestructible. That's just not realistic.
For sure. So we start off slow, again, kind of going back to what I was talking about, getting a pre-existing fabricated arm. A lot of times I'll use weight as a good baseline. And then between the weight and the stress testing, we can see if there's any stress risers, and we could remove or add material in areas that are prone to stress. And then from that point, we use weight as a gauge. So naturally the weight or the strength to weight ratio on 70-75 is going to be greater. So we can start off at like 20% less weight overall when the part is done. And then from that point, we can add or take away depending on which direction we want to go. So we've been continuing to decrease the weight to a point where we're happy. And right now we're taking about 25% of the weight out of a conventional steel arm. So that's great weight savings in the right place.
Yeah, particularly as you say, the savings in the unsprung weight is going to allow the suspension to do its job better. One of the aspects with a material like aluminium 70-75, which you say you're using there, as I understand it, and please accept here, I'm definitely not a metallurgist, is that it does have a fatigue life as a potential issue, which a chromoly arm is not as susceptible to fatigue-related failure. Am I right on that? And if so, how do you sort of deal with that fatigue aspect with the alloy material?
Yeah, I don't believe that it's greater. Sheet metal arms, they're welded together. And with the amount of damage that they get, rather than, getting a little piece cut out of it, like the aluminum would chip away, more or less. The steel, it kind of starts to mushroom and wants to separate from its construction. And especially if water gets in it, then it can rust from the inside out. So overall, I think aluminum is a greater option for sure.
Sure. Okay. In terms of the design for suspension components particularly, do you go through, how are you designing or developing the kinematics, the movement of those arms, etc., to optimize the suspension geometry through travel? Because obviously these pre-runners have got massive amounts of suspension travel as well. Is that a concern? How are you dealing with that?
Yeah, so all of that's done in Autodesk Inventor. Or in, like anybody else in the industry, it's all done through the computer. So we have we have our travel numbers, we have our track width, we have our wheelbase numbers, and using all of these factors, we'll start off like the front end. For example, I might start off with like the spindle, set the kingpin angle, the wheel offset, make sure my scrub radius is where I want it, check the track width, and then from there, once that's set, a lot of the times I'll start constructing geometry for my lower arms, and then after that, we'll basically have a good idea of where we want our camber curve to be, essentially where that camber is going to be through that full range of motion. And we're dealing with nothing but travel, anywhere between 19 to 24 inches of travel on the front, full suspension travel, upwards to 33 inches of travel on the rear. And so we want to make sure that when it's going through that range of motion, that camber curve is, and the truck's tilting, that's going to have a good foundation to sit on when that whole truck is moving around, because there's a lot of movement going on. So we'll set all of the camber curves and then look at the caster and the caster curve and all that stuff. And then from there, I think the last thing we usually do is just set the Ackerman, the steering. And a lot of times when we do the steering, we'll make sure that the bump steer is correct through the range of motion, and then kind of go through there. And then I'm also speaking on full truck builds. These are not retrofit like production stuff. This is like ground up for the most part. It's a little different on pre-existing applications. Like if you have a truck that needs a long travel kit or something like that, you have to work around parameters that are already pre-existing. But if
something more of a compromise,
yeah. But our chassis, we're allowed full realm on every aspect. So we do everything. It's 100% ground up. It's all proprietary, and it's all the geometry that we like and we see that works the best. And so we'll set all those numbers and boundaries in place. And then once the suspension is being cycled in geometry, then we start building and fabricating, the uprights, the lowers. We make sure that there's no interference. We'll steer the truck left and right through the full range of motion. We'll put everything in the drawings, everything from the pump, the steering arm, the steering boxes, everything to show exactly what's going to happen, make sure everything's bumped out, fully drooped, and that we're seeing all the numbers that we want to see before we even start any manufacturing part of that.
So this would be one of the big advantages of developing the entire truck in 3D first before anything's actually manufactured, is, as you say there, you can move the suspension through full droop,
yeah.
and compression, and then full articulation of the steering, and essentially ensure that you're going to have no interference with any of those components, where I'm sure in the past many people have been caught out by something they didn't anticipate once they actually are sort of pretty deep into the fabrication process. Obviously that's a waste of time and a lot of money if you sort of have to redesign something that's already partially built, correct?
Yeah, definitely. And these trucks are pretty big, but man, you'd be surprised. Packaging is always a nightmare. I feel like you can never get away from that. Packaging your arms and your shock packages, especially with the shock packages getting so much larger these days. You have 4.5-inch bypasses with IBP reservoirs, and the shocks are massive. I don't know if you've ever seen one in person, but they're humongous. And fitting all those shocks and the steering and cycling it all and make sure these tires are not hitting the cockpit. It's still a bit of a challenge. And having the computer to do it for you, or having the computer as an aid, it's really nice because you can start fabricating your arm, and then you might see that your upright might have a little bit of issue when it's at full bump, at full steer or something. And you can clearance out your spindle, or you can choose to redesign your arm a little bit so that it has just that right amount of clearance, and everything comes out perfect. I mean, I have some guys ask me like, well, how do you trust like it's going to be exactly what's on the computer? It's pretty dang close. Like, you would be surprised. It's like, thousandths, it's ridiculously accurate.
When you're cycling the suspension like that, or moving the steering, is it your responsibility to sort of zoom in the areas that you think there might be some interference and physically check the clearance, or will Inventor actually tell you, hey, warning, there's a clash here, this is hitting this?
Yeah, so you can have, so me personally, I don't do that. I would just look at it because I can see clearly what's going on or not. But in my, when I'm designing something, I'll make sure that all my constraints are in place. So the shocks are fully constrained to their full limitations. They're going to be not collapsing or extending further than they're actually going to be doing in real life. The steering isn't going past any extents. You'll set all your extents on your steering and your suspension. So you can lock it out. You could fully bump it out. And you don't really want it to be to where it's like, oh, it's touching barely. You usually want some room in there. And so you can measure that. And so a lot of the times you don't need to have any kind of interference problem solver, intuitive computer telling you to do this or that. You just know, you can see it right away and everything's set. So as long as all your constraints and your limitations are set correctly, you should have no problem visually seeing what's going on. And visually, you can measure it also. You have tools there to measure, how close you are to one thing. And a lot of times, I'll set stuff to it where it's only a quarter inch away from hitting and be comfortable with that.
Now, one aspect here is of manufacturing the complete truck is obviously these components that get machined, but there's also the tubular structure for the actual chassis and the rollover structure, etc., engine mounts, everything else that goes into a complete vehicle. When you've developed this model and you're basically ready to hit print and produce the finished vehicle, does the chassis components, the tubular chassis components, do these get CNC bent and notched as well?
Yes.
Based on your model, or is this hand fabricated?
No. So generally speaking, if we're talking just like CAD models to real life, everything is laser cut. So it's laser cut and CNC bent. A lot of the new machines that are coming out, they have the ability to roll and bend. So you can add rolls into your weldment features or your chassis design, and then you can have them basically transition to a bend if you'd like. So you can get a little bit more intricate with your designs. But for the most part, everything that's done on the computer is 100% CNC cut and bent.
Okay, so again, you can guarantee essentially the finished product is going to fit and look exactly like your model.
Yeah, and like I said, depending on who's doing it, we've had some cases where they're a little off. The benders aren't going to be exactly the same, but there's some guys that they can get it right on the money. But that's why we also use fixtures. So the fixtures, we design the tables and we have towers that we mount to the fixtures, and these fixtures are reassurance that everything is going to be exactly where it's at in the computer. So between the CNC bending and the CNC cutting, the fixtures hold everything in place, and it's very important for the fixtures to be there anyways, because when you weld it, the materials are going to heat up and they're going to want to move around on you. So the fixtures hold everything in place. So there'll be a lot of fixtures that go into the design process as well. And then essentially that's just there for keeping them in place while they're being welded, and also making sure that everything is 100% accurate to the computer.
If anyone wants to sort of get a better understanding of what these fixtures are, a bit of a dive through your Instagram feed will show those up. And I've seen again on your Instagram, you've got those fixtures essentially attached to your fixture table, which is a nice flat surface that acts as a reference plane. So you've got those basically going to locations where there'll be, for example, a trailing arm will attach. So it's a way of ensuring that in space, those components are fitted in exactly the right location, correct?
Yeah, exactly. Yep. And yeah, the actual Instagram, there's a few pictures. If you kind of navigate through them, it'll show the process. And I try to do a lot of that with my Instagram. Try to show like a nice shot in the beginning, and then if you click on it, you can kind of storytell, kind of you kind of go through. You see the design, and manufacturing process behind it.
I appreciate that. Getting that understanding rather than just looking at a pretty picture and scrolling on to the next Instagram feed of a cat jumping off a couch or something stupid. It's nice to get that more in-depth understanding of actually what's going on. Though, am I right in saying that you're actually developing the fixtures themselves as in CAD as well?
Yeah.
So everything's sort of developed around the same process.
Yeah, everything's done in the computer. Yeah, so it's not something that you can open a catalog and just order everything, which would be nice. But no, it's all just kind of thought out, and you look at, you try to find a design for the fixture table and everything that's going to be continually used for the next projects to come. Maybe use some primary fixture components that can be reused so that you don't have to constantly cut really large pieces of fixtures, rather just attach, So yeah, all that's, it's designed in the computer, it's drawn in the computer, and then when those get manufactured, those are accurate as well, just with the drawings of the trucks as well.
Okay. Straying away a little bit from the actual 3D modeling side of things, but just getting into the fabrication, the material that's being used for the construction of the chassis, is this all chromoly?
Yeah, it's 100% chromoly. As a matter of fact, I don't think there's any mild steel in the shop, or there might be a sign that says no mild steel allowed. But everything is 4130 chromoly, 100% in the shop.
All right, so my understanding there is essentially, if we compare a mild steel to chromoly, the strength is significantly greater, which means that you can use a thinner cross-sectional area, thinner wall thickness in the chromoly material compared to mild steel in order to get the same strength, but at a weight advantage. Is that about correct?
Yeah, 100%. Yep. It's definitely, because of its higher strength, we are using thinner walls than what you would typically use like in a DOM application. It also, it burns a little different too. It welds different. It welds a lot cleaner than mild steel would. The TIG welding, for example, that the guys are doing, that's how you get those like really brilliant colors and like all these super nice welds. It's because the chromoly melts a certain way where the rod and that material, they just work really well together.
One of the concerns around the chromoly fabrication is around the welding, and particularly it's a material that's not very forgiving if you are using excessive heat. And over the years, we've seen numerous examples of roll cages that have actually shattered on impact because the chromoly, if it's overheated, can become brittle, essentially around the heat-affected zone either side of the weld. So there's a lot of this come down to welding technique, knowledge on the part of the welder, and fit up to avoid the potential for those sorts of issues.
Yeah, I mean, the welders that we have at the shop, they're very experienced, and they have a way of working with their welds and whatnot. But they do tend to do like multiple passes on some of the welds. Like they don't just do they won't just do one weld on most of the chassis. It'll have a root weld, and then it'll be cleaned, and then like wire wheeled, for example. And then after that, it'll go through for a second pass. I can see what you're saying. I feel like if you're inexperienced and you're sitting there with the torch and you're just kind of working your way around there, if you let that heat line just really just flow out of there, then you could be causing some damage to the material. But for the most part, I mean, you can see clearly that the welds are nice structural welds because the heat lines are really nice and consistent. They're not really far out. You're not having like the graining, when the welds turn really gray, you're not having discoloration like that. So there's a lot of things, but most of it comes down to the person that's welding it and their experience in welding the material, for sure. Yeah.
Okay. In terms of the sort of abuse that these trucks are seeing in competition, and you mentioned earlier sort of 1,000 miles of competition use over some pretty gnarly terrain, do you sort of have a life on any of the components, or does that safety factor that we discussed before, you've basically got enough excess strength that nothing needs to be replaced unless it's physically been damaged for the life of the truck?
Yeah, they'll have prep, so like during prep, if something looks damaged or out of place, like it needs to be replaced, they'll replace it at that point. A lot of the times the areas that get affected the most are rod ends or hinds. They tend to wear out and need to be serviced more often than anything. But most of the times you'll look at a part for any kind of structural fractures or anything like this, or tearing, or if you hit something really hard, then we'll tear it down or something like this. But for the most part, it all comes down to the prep, you know.
In terms of the experience you've had, it's really vast now in the industry, and I'm sure you've seen numerous vehicles from home built through to some of your competitors. Are there any sort of consistent engineering fails that you see of design elements that people just should not be incorporating into a vehicle? Any sort of tips for our listeners of what not to do when you're designing maybe a suspension arm or a component of that nature?
Oh man, that's a hard one. I don't know, because everybody's so opinionated. I would hate to say something's wrong from right or right from wrong, you know? I think everybody has their own beliefs, especially in the off-road industry. Everybody has their own beliefs on how things should be made. And that's fine. Everybody's entitled to their own opinion because, that's how we evolve in any sport, is people thinking out of the box. So I wouldn't condone anybody for any design realistically. As far as anything that's breaking, I think the only things that break are the fairly obvious ones, But when you start off, I think the hardest part to start off in designing for like trucks, for example, is the understanding of, like the thickness of materials that you need to use for the application, and what kind of cross sections you might need for like inner structures of sheet metal products, or even chassis layouts. I do think that one of the areas that tends to be a problem is if the roof isn't laced correctly, and it doesn't. A lot of times, if the upper tubes on the roof don't lace out to the A pillars, that there's a chance that roof can collapse on you in an accident.
Okay,
but
definitely
that's
not what you want.
Yeah, but that's again, most of these guys are doing that right anyway. It's just one of those things. Most of the guys are just are figuring it out and going out there and taking what they have and making it happen. And there's nothing wrong with that.
One of the more common issues I do see is people designing a suspension component or a suspension arm where they've inadvertently end up using a rod end or a heim joint, as you've referred to them, and place that in bending, which, again, it's one of those situations where plenty of race cars are getting around with a rod end located so that it's subjected to a bending force. But in the perfect world, ideally we want to try and stay away from that. They're not really as strong in bending as they are in compression and tension, correct?
Yeah, rod ends, the rod ends that we're using on trucks are so much more massive than the ones that you guys are using in your motorsport stuff. I don't know how you guys even use your rod ends for your suspension or trust them. But the rod ends that we have, they are burly. They feel like a stone in your hand. So yeah,
we also try not to hit massive boulders at 100 mile an hour.
Right.
That's one of the ways we get around that.
Yeah, I don't know. I think like a 3/4 inch rod end has some sort of 30,000 pounds of radial load, and these rod ends that we're using are way bigger than those. So yeah, these you don't. I see what you're saying. I know exactly what you're talking about. We don't have that inherited problem in trucks as far as bending rod ends. Like most guys have in cars doing that because they're just so freaking strong.
Sure.
So you don't have to worry about the angle of the rod end. It's not as critical as you would think, like in comparison to a car where they're using lighter weight rod ends.
Okay. All right. Now, a lot of people listening to this are obviously going to be interested in learning some of the skills, just scraping the surface of some of the skills that you've developed. And I'm just wondering if you could give maybe a few pointers for those who want to start developing skills in 3D modeling. What's the easiest way to get started, and what advice could you give there?
A lot of it comes down to practice. There's not enough seat time that you can put in to actually designing. I have a lot of seat time. I've been doing it for a long time, like I explained, since I was a kid. But even the last couple of years, I'm on my computer a lot, sometimes 14-hour days, taking breaks in between 6-7 days a week. So, every single time I'm on my computer and I'm drawing something, I'm always learning or figuring something else out to add to like my belt, so to speak. So I think it all comes down to just seat time. If you want to do it, you can do it for sure. You just got to sit down. You got to put the time aside to do it.
I think that a lot of that comes down to getting your priorities aligned with what you really want to be doing. I'm interested though, because it sounds like you've also had two sides to this coin in terms of you started with the high school CAD courses, so you've got some actual high school level training.
Mm-hmm.
Then it sounded like you spent a huge amount of your own time just testing, developing, and learning by yourself. And then you went and did the solid modeling, again, an actual structured course. What would you say is some actual structured training around this essential, or is that just something you're going to need if you want to get to a certain level?
Well, there's always YouTube Academy is what I like to call it. Basically, you spend a ton of time on YouTube figuring it out. But man,
definitely,
there are some things that I learned going to trade schools that you cannot learn on YouTube. And so if you were really serious about, learning a little bit more, I'm not talking about going and getting like a degree like we talked earlier, but there's a lot of trade schools out there that are accessible either online or even at a local college or locally everywhere. You just got to reach out to them and see what they have to offer. And sometimes it might not be exactly what you want, but you still should sign up for them and do them because, again, when I took the courses with Cative Technologies, some of the stuff that they taught me, there's no way I would have been able to figure that out on my own. And not that I even used that information, but it was a foundation. And the same thing goes for like my computer graphics class that I took at the college. Yeah, you can use Photoshop, you can use Illustrator, but they show you the fundamentals. They show you what kind of file extension you need to be using for this certain thing, or what a vector file is, or anything like that. All of that kind of coincides with what I do today now, because had I not had that foundation, I wouldn't be doing or outputting the illustrations that I can today. And so it's been kind of like a collective effort of all the things that I've learned combined to kind of put that out. And as far as, I know you were talking about the rendering, you're like, well, what rendering software do you use? And I get that a lot. I don't use any rendering software. It's a screenshot, essentially.
Wow, okay.
Yeah, people get blown away because they're like, what do you mean? Well, I've been messing with colors and layers and materials since I was in high school. And so when I started getting more efficient at Inventor, I kind of just always did that. I just said, I'm going to apply the right material to this, apply the right material to that. And it would just get under my skin, maybe OCD. I'm like, well, that bolt's not the right color, So then eventually the whole drawing, you got 1,000 files and every single thing's colored the right way. And then that makes a really nice illustration. And fortunately, the backdrop you preset, and basically the whole thing that I do is all presets, for the most part. I preset it, and it's been kind of evolving over time, but it's nothing too crazy. It's like I said, it's a screen grab, and that's the pictures that you see is actually the interface that I work on day in and day out. So you guys see the pictures of the nice drawings. Well, I'm seeing that through my work environment every day. But yeah, it's just kind of like I set it all up and I grab a picture and everything's just preset. And I'm very meticulous about every little detail of it. I used to render a lot. And I respect all that because that takes a lot of time and I'm familiar with that process. But when I try to render on Inventor, it comes out worse. So I was like, I don't like the render processing part that Inventor offers. So I'm like, the next best thing is I just want a screen grab. I'm also very keen on like getting the right shot. So I like photography. And so like a lot of the times when I take a picture of like something I'm illustrating, I visualize actually taking a picture of it in person. It kind of gives a nicer view of what I'm doing. So again, it's all collective. Like it's everything I've done in the past and present, and just kind of, that's just how it comes out. There's no like real big secret on it.
One question that sort of comes out of that I probably should have asked a little bit earlier. Everything that you produce, you sort of look at these screenshots that you're posting to your Instagram, and I mean, everything just looks visually amazing. The components that you're designing, when you are designing them, sort of what consideration are you taking for the aesthetics or how that part looks versus just pure raw functionality? Because, I mean, you could have two parts that, for all intents and purposes, serve the same task and do an adequate job, but one looks great and the other just looks rough and ugly, essentially.
Yeah, I guess I have a very unique styling cue when it comes to certain things. I like a lot of draft angles. I like a lot of like aesthetic feel to the parts. It makes it more challenging to produce when you're manufacturing it. It's harder to machine. It's not. I definitely don't make my own life easier. I tend to make it harder for some reason. But it's always cool to actually make these things come to life. But a lot of the times, yeah, I'm not really like drawn to like conventional machined parts. I get a lot of inspiration through like motorcycles or even Formula One, and depending on what it is, even architecture. So it's kind of like modern warfare kind of like weapons look to it. But I like a lot of draft angles, and a lot of times I like things to kind of have a nice shape to them no matter what. So I mess with them quite a bit. I think people feel like, oh, he just came up with this, but some of it takes a lot of effort, and a lot of the parts I've designed, I have 6 or 7, renditions of that part to eventually come out to the outcome. So it's not like the first time it was all done. And sometimes I take a break for a day or two even, so sometimes I'll start a project and I'll get a little bit of brain fog, and I'll say, I don't push myself. I say, okay, I'm going to go on to another project. And when I come back in a day, I'll look at it with fresh eyes and I'll continue working with it. So I'm kind of going in and out of a lot of projects like that.
Okay. In terms of the tools that you've got at your disposal at the moment, is there anything that you wished you could do that the current technology is really holding you back on?
I don't know. There's a lot of cool stuff out there. And fortunately at our shop, we have really cool machines, we have really nice welders. We have nice tools. We have the UMC 1000, which is our 5-axis CNC machine. We have a 3-axis mill, 2-axis lathe. We're adding a tube laser cutter in the next month, and we're also adding a laser bed for actually cutting all the sheet metal. And we're also adding a CNC bender as well, all in the next month. So we'll be pretty well equipped at our shop. But as far as industry is concerned, I think really the only thing we're lacking on is accessibility to 3D printing metal. I think that would be cool to access more often, but that's going to eventually come out, with time. So
yeah, no doubt. Just like the plastic 3D printers, it'll come down in cost significantly and become much more accessible.
Yeah, it's like the movie Jurassic Park. I think in the intro, the guy 3D prints the esophagus of a dinosaur, and they're like, "We're going to emulate this sound." And and watching that as a kid, you're like, "That'll never happen." And now everybody's 3D printing, phone charge holders or something funny. I don't know.
All right, Matt. We'll move towards wrapping this thing up. It's been great so far. Huge amount of information in there, and we really do appreciate you taking time out of your busy schedule to give us all of that deep background. We've got 3 questions we ask all of our guests here to wrap up, and the first of those, and maybe we've touched on a little bit of it there as well, but what sort of next for you in the future, either you personally or you and Kibitech?
Yeah, so I mean, in the near future, we have a lot of plans for the business. There's a lot of new trucks that we're adding. We're venturing off a little bit from off-road in some applications. We have a couple projects that I'm super excited to show in the next couple months that I've been working on that aren't off-road related, but they will be actually being manufactured through the business. And unfortunately, I can't say anything yet, but you guys will see it in the future.
Watch this space.
Yeah. And then as far as personally, there's a few things I want to add. I'd like to eventually start a small community or website where, students or people can have a smaller outlet for CAD related things, but that'll probably be in about a year or so. So kind of still collectively thinking about some things that would be cool to add. Kind of like how you guys are doing, just on a smaller scale, just CAD related little things. But some of the more stuff that people have been asking for, and just kind of giving back a little bit to the CAD community as much as I can. But
I'm sure people will be eating up anything that you put out.
Yeah, and then Kibitech has been doing a great job with their YouTube videos, so I've been trying to put a little more input into that as well. And their media guy is just amazing. So, but yeah, I mean, all of this is I'm definitely grateful for Kibitech for giving me the opportunity. I feel like more companies should give people opportunities for sure, and trust that if they believe in their employees, that they could evolve into something great. I owe him a lot because I don't think that I'd be here talking to you if it wasn't for him giving me an opportunity to kind of show what I can do. It's been a long journey for myself, but it's been a lot of hard work. And I would say that's the other thing is anybody can do what I'm doing. You just got to put in the time. You got to put in the effort. You got to put in the work. And it just comes with time. You just keep on doing it. You're consistent about it, and it'll come. But if you like it, just keep on doing it.
Well, it sounds like that's probably the answer to our next question. Maybe you've got some more insight you want to add. Our next question is looking at your career so far and everything that you've achieved, everything you've learned and everything you've done. Is there any advice you'd give to a younger version of yourself to sort of fast track that progress?
Yeah, definitely. Like I said before, I think school is very important. Had I had a little bit more guidance growing up, I feel like I probably would have just started off in the direction in mechanical engineering and skipped about, 8 years of hard work and labor, figuring it out secondhand or through peers. But I'm grateful for everything and everywhere I've gone through and all the experiences I've had. But overall, yeah, I think I'm also grateful for every student that reaches out to me. And I have a lot of people that reach out to me on Instagram. And that's one of my favorite parts of Instagram is the students from different universities always asking me like how I got where I'm at. And I always think like, man, you guys are in such a better position already by being in school and getting in that direction that I feel like my advice is nowhere near as good as where you're already heading. And like I said, had I had more hindsight of what I'm doing today, I would have stayed in school and probably stayed a little bit more focused on that. But like I said, even with schooling, you still need to put in the work. So no matter what, you got to dedicate yourself to the trade and definitely put in the time. And that paper is only going to do so much for you. You still have to put in the work for sure.
Yeah, there's unfortunately no substitute for, as you put it earlier, the seat time. You just need to physically be on the tools, whatever that may be, a TIG welder, a laptop keyboard, or in your case, 3D modeling software.
Right.
All right, last question for today, Matt. If people want to follow you, and I 100% urge that they do, great account to follow on Instagram. Where can they do so? What are your social media outlets?
Yeah, primarily right now is just on Instagram, and it's Matt_826, and 8 is spelled out EIGHT, and then the number 26. But yeah, that's my main outlet for most of my content. Eventually might start up and add a few more like the Twitter stuff and who knows, maybe TikTok. There's enough cool action going around the shop where these trucks are just flying in and out of there and they're just being built and they're super cool to look at. And maybe even add more CAD stuff on that. But for the most part, just Instagram for now.
Okay, perfect. And we'll put a link to your Instagram account in the show notes as well, so people can't miss that. Look, Matt, been great to chat, and thanks again for your time. We really appreciate it, and all the best for the future.
Thanks, Andre. I appreciate you.
All right, that concludes our interview. And before we sign off, I just wanted to mention for anyone who's been perhaps hiding under a rock and hasn't heard of High Performance Academy before, we are an online training school and we specialize in teaching a range of performance automotive topics, everything from engine tuning and engine building through to wiring, car suspension and wheel alignment, data analysis and race driver education. Now remember, you've got that coupon code. You can use podcast75 at the checkout to get $75 off the purchase of your first course. You'll find our full course list at hpacademy.com/courses. Important to mention that when you purchase a course from us, that course is yours for life as well. It never expires. You can rewatch the course as many times as you like, whenever you like. The purchase of a course will also give you 3 months of access to our gold membership. That gives you access to our private members only forum, which is the perfect place to get answers to your specific questions. You'll also get access to our regular weekly members webinars, which is where we touch on a particular topic in the performance automotive realm. We dive into that topic for about an hour. If you can watch live, you can ask questions and get answers in real time. If the time zones don't work for you, that's fine too. You're going to get access as a gold member to our previous webinar archive. We've got close to 300 hours of existing content in that archive. It is an absolute goldmine. So remember that coupon code podcast75. Check out our course list at hpacademy.com/courses.